So in this section, we'll go ahead and introduce the idea of solving a linear system of equations using substitution. So down below, I've written out the steps that you're going to need to use to solve a linear system of equations on two variables using substitution. Instead of repeating this out loud, let's go ahead and just look at some problems using this method. In our first example using substitution, we're going to solve the following linear system. And what we're going to go ahead and do is let's call this equation 1, and we'll call this equation 2. So for equation number 1, let's add a 2y to both sides, and our linear system becomes x is equal to 2y minus 1. And nothing changed for equation 2, so we still have the following. And now what we're going to go ahead and do is we're going to replace our x value here with our 2y minus 1 up top, and so our linear system becomes equation 1 remains the same, but equation 2 is now 4 times 2y minus 1 minus 3y is equal to 16. So simplifying equation number 2, what we're going to get is 8y minus 4 minus 3y is equal to 16. And now we're going to go ahead and simplify equation number 2, add our y's together, and then add a 4y to both sides. And equation number 2 then becomes 5y is going to be equal to 20. Now dividing both sides of equation number 2 by 5, this is going to go ahead and give us that y is equal to 4, and our x is still equal to a 2y minus 1. So go ahead and plug in y is equal to 4 into equation number 1, and what we end up getting is that our x value is going to be equal to 8 minus 1, and our y value is equal to 4. So therefore, our solution is going to be given by x is equal to 7 and y is equal to 4. So let's go ahead and identify what kind of linear system this is. So again, we're given two equations. So again, let me go ahead and reiterate that this is just a schematic of what our lines look like. So we have one red line and one green line. They have one intersection point, which is given by the point 7, 4. And so therefore, we have a consistent system with one unique solution, and so therefore, this is an independent solution. So before we look at another problem, let me go ahead and just state that substitution has its pluses and minuses. It's very easy to use for linear systems with not many equations and not many variables, but what we'll see in section 7.2 is that elimination is going to be far more useful for solving linear systems of equations. So let's go ahead and look at another example using substitution. And again, we're going to go ahead and solve the following linear system. So we already have one of our equations written in terms of y, so let's go ahead and replace our y in our second equation with 3x plus 2. Again, nothing goes on with equation number 1, this is still 3x plus 2, but equation number 2 is going to become 4 times 3x plus 2 is equal to a 12x plus 7. So simplifying equation number 2, what we see is that the left-hand side becomes a 12x plus a 8, and this is equal to 12x plus 7. So subtract a 12x on both sides, and equation number 2, we see that this is going to just be then a 8 is equal to 7. And so this doesn't make any sense. And since we get a nonsense answer, this tells us that our solution does not exist. We have an inconsistent system. So another way at looking at this problem is we can go ahead and graph what this system represents. To graph this system of equations, we're going to leave y is equal to 3x plus 2 alone, but go ahead and divide 4 on both sides for equation number 2. So then we'll get y is equal to a 3x plus 7 divided by 4. And we're going to let our red line be equation number 1, so we have 3x plus 2. And we'll let our black line be equation number 2. So this is 3x plus 7 divided by 4. And both of these have the same slope, so therefore these are parallel lines and they never intersect. So this is an example of an inconsistent system. And again, it has no solution. Let's look at one more problem using substitution. And we want to solve the following linear system. Again, let's go ahead and this time let's subtract an x on both sides for equation number 1. Equation number 1 then becomes y is equal to a negative x plus 5. And replace our y variable here with a negative x plus 5. Equation number 2 then becomes a 2x plus 2 times a negative x plus 5, and this is equal to 10. So simplifying equation number 2, we're going to get that 2x minus 2x plus 10 is equal to 10. So our 2x's cancel out, and we're left with that 10 is equal to 10. So this is a little bit of a strange phenomenon. But what this is saying is that we're going to have an infinite number of solutions. It looks a little strange here. So maybe let's go ahead and interpret this a little bit differently. Let's solve both of these equations for y real fast. So equation number 1, as we've seen before, is going to be y is equal to a negative x plus 5. And subtract a 2x on both sides for equation 2, then divide both sides by 2, and we see that we're going to get y is equal to a 2x negative plus 10 divided by 2. So simplifying this one more time, our equation number 1 is negative x plus 5, and equation number 2 is going to be a negative x plus 5. And so even though it didn't look like this, both of these equations that we were originally given are the same equation. One is just a scalar multiple of the other. And so what this tells us is that even though we have two different equations, they're actually the same line. And so we have a consistent system with infinitely many solutions, and so this has a dependent solution. So depending on what book you're reading, you can write this solution in many different ways. I think one of the simplest ways that people usually write this is as the following. We have our x is going to be equal to our x values, and our y value is going to be equal to a negative x plus 5. Another way to write this is in terms of a point. So to write this as a point, we'd write this as x, comma, negative x plus 5. And so in both cases, if we wanted to find a particular solution, we just plug in whatever number we want for x. So for example, let's plug in the number 3 for x. And then our y value becomes a positive 2. And so this is a specific example of one solution out of infinitely many. And this solution be represented by this point on our graph, somewhere over here, the point 3, 2.